The splitting of atomic nuclei is called nuclear fission. Nuclear fission involves the balance between the nuclear strong forces and the electrical forces within the nucleus. In all known nuclei, the nuclear strong forces dominate. In uranium, however, this domination is tenuous. If the uranium nucleus is stretched into an elongated shape, electrical forces may push it into an even more elongated shape. Nuclear deformation leads to fission when repelling electrical forces dominate over attracting nuclear forces. The absorption of a neutron by a uranium nucleus supplies enough energy to cause such an elongation. The resulting fission process may produce many different combinations of smaller nuclei. The fission of one U-235 atom releases about 7 million times the energy released by the explosion of one TNT molecule. This energy is mainly in the form of kinetic energy of the fission fragments. In a typical example of nuclear fission, one neutron starts the fission of the uranium atom, and 3 more neutrons are produced when the uranium fissions. Most nuclear fission reactions produce 2 or 3 neutrons. These neutrons can, in turn, cause the fissioning of 2 or 3 other nuclei, releasing from 4 to 9 more neutrons. If each of these succeeds in splitting an atom, the next step will produce between 8 and 27 neutrons, and so on. A chain reaction is a self-sustaining reaction. A reaction event stimulates additional reaction events to keep the process going. Chain reactions don't occur in uranium ore deposits. Fission occurs mainly for the rare isotope U-235. Only 0.7% or 1 part in 140 of uranium is U-235. The prevalent isotope, U-238, absorbs neutrons but doesn't undergo fission. A chain reaction stops as the U-238 absorbs neutrons. If a chain reaction occurred in a chunk of pure U-235 the size of a baseball, an enormous explosion would likely result. In a smaller chunk of pure U-235, however, no explosion would occur. A neutron ejected by a fission event travels a certain average distance before encountering another uranium nucleus. If the piece of uranium is too small, a neutron is likely to escape through the surface before it finds another nucleus. Fewer than 1 neutron per fission will be available to trigger more fission, and the chain reaction will die out. The critical mass is the amount of mass for which each fission event produces, on the average, 1 additional fission event. A subcritical mass is one in which the chain reaction dies out. A supercritical mass is one in which the chain reaction builds up explosively. 2 pieces of pure U-235 are stable if each of them is subcritical. If the pieces are joined together and the combined mass is supercritical, we have a nuclear fission bomb. A simplified diagram of a uranium fission bomb is shown here. Building a uranium fission bomb is not an excessively difficult task. The difficulty is separating enough U-235 from the more abundant U-238. It took more than 2 years to extract enough U-235 from uranium ore to make the bomb that was detonated over Hiroshima in 1945. Uranium isotope separation is still a difficult, expensive process today. A liter of gasoline can be used to make a violent explosion, or it can be burned slowly to power an automobile. Similarly, uranium can be used for bombs or in the controlled environment of a power reactor. About 19% of electrical energy in the United States is generated by nuclear fission reactors. A nuclear fission reactor generates energy through a controlled nuclear fission reaction. These reactors are nuclear furnaces, which boil water to produce steam for a turbine. 1 kilogram of uranium fuel, less than the size of a baseball, yields more energy than 30 freight car loads of coal. A nuclear fission power plant converts nuclear energy to electrical energy. A reactor contains 3 main components: the nuclear fuel, the control rods, and water. The nuclear fuel is uranium, with its fissionable isotope U-235 enriched to about 3%. Because the U-235 is so highly diluted with U-238, an explosion like that of a nuclear bomb is not possible. Control rods that can be moved in and out of the reactor control how many neutrons are available to trigger additional fission events. Control rods are made of material, usually cadmium or boron, that readily absorbs neutrons. Heated water around the nuclear fuel is kept under high pressure and high temperature. It transfers heat to a second, lower pressure water system, which operates the electric generator in a conventional fashion. A major drawback to fission power is the generation of radioactive waste products of fission. When uranium fissions into two smaller elements, the ratio of neutrons to protons in the product is too great to be stable. These fission products are radioactive. Safely disposing of these waste products requires special storage casks and procedures. When a neutron is absorbed by a U-238 nucleus, no fission results. The nucleus that is created, U-239, emits a beta particle instead and becomes an isotope of the element neptunium. This isotope, Neptunium-239, soon emits a beta particle and becomes an isotope of plutonium. This isotope, Pu-239, like U-235, will undergo fission when it captures a neutron. The half-life of Neptunium-239 is only 2.3 days, while the half-life of Plutonium-239 is about 24,000 years. Plutonium is radioactively toxic. It's more toxic than uranium, although less toxic than radium. Pu-235 emits high-energy alpha particles which kill cells rather than simply disrupting them and leading to mutations. The greatest danger that plutonium presents is its potential use in nuclear fission bombs.